Look at this image of clear ice encasing fruit blossoms. During a late spring freeze, sensitive reproductive tissues are trapped in a lethal thermal envelope. The economic toll of these events is severe. In April 2025, a massive frost event struck Turkey, dropping temperatures as low as -15 degrees Celsius. This single event wiped out agricultural production across 36 provinces. This damage occurs because perennial crops are caught at their most vulnerable phenological stages, specifically bud break and flowering. When temperatures hit even -2 degrees Celsius at full flowering, as you can see in this close-up, irreversible reproductive failure begins, indicated by the onset of petal damage. Climate change is actively worsening this risk. Rising average temperatures are pushing spring phenology forward, causing plants to break dormancy significantly earlier in the year. However, the dates of the final spring frosts are not receding at the same rate, leaving a wider window where active growth overlaps with freezing conditions. The physical results of this exposure are immediate. Young vegetative shoots are highly sensitive due to their high water content and thin cell walls. Look at this grapevine foliage. After freezing, the tissues rapidly become necrotic, turning shriveled and brown. Late spring frost acts as a multifaceted stressor. It disrupts immediate photosynthetic capacity, halts the development of young fruit, and depletes the plant's energy reserves, compromising the reproductive yield for both the current and subsequent seasons. While frost destroys crop viability in the vineyard, a completely different biological reality plays out on the coniferous forest floor. Here, a drop in temperature acts as a catalyst rather than a catastrophe. This environment is home to the basidiomycete Hygrophorus hypothejus. It is commonly known as the Herald of Winter because its fruiting bodies appear exclusively after the first overnight frosts of the season. This specific timing provides a distinct evolutionary advantage. As shown here, the mushroom emerges from a frost-whitened forest floor. Freezing temperatures thermally suppress competing saprophytic fungi and potential parasites, leaving the habitat open. Biologists call this state the winter niche. The extreme thermal conditions create a competitive vacuum, allowing cold-adapted chemical specialists to monopolize available resources without interference. To understand exactly how frost destroys a crop while sparing specialized fungi, we must examine the biophysics of cellular failure. This diagram of a plant cell environment shows jagged ice crystals growing in the extracellular spaces. Frost death is driven by this extracellular ice formation rather than the absolute drop in temperature. As pure water freezes outside the cell, it lowers the extracellular osmotic potential. Notice the blue particles representing water molecules migrating across the cell membrane toward the extracellular ice. This movement is driven by a pressure gradient, attempting to balance the osmotic differential. This continuous outward migration results in severe intracellular dehydration. The plant cell loses its internal water volume, placing an immense mechanical and osmotic stress on the selectively permeable membrane. The terminal point of failure occurs within the membrane itself. In this molecular visualization, watch how the fluid lipid bilayer rapidly locks into a rigid, brittle geometric gel lattice. This process is known as a lipid phase transition. Once the membrane reaches this gel state, it loses its structural integrity. The cell experiences terminal electrolyte leakage, where vital intracellular sugars, ions, and protective compounds bleed out through the ruptured barrier. Frost-induced death in vascular plants is ultimately a biophysical process. It is a structural collapse of the membrane, triggered by extreme osmotic dehydration and lipid crystallization. Agronomic practices attempt to physically intercept these cellular failure points by manipulating local thermodynamics to keep plant tissues above that lethal phase transition threshold. One traditional method relies on direct thermal radiation. This vintage photograph shows an operator running smoking orchard heaters, which burn fuel to physically increase the ambient air temperature immediately surrounding the trees. Yet another approach addresses the atmospheric conditions. This silhouette against a foggy field shows a wind machine. These operate during radiation frosts to break up temperature inversions, pulling warmer air from higher altitudes down to the ground level where the crops sit. Growers also utilize the latent heat of fusion. Here, irrigation wheels spray water continuously over the crops. As the water freezes into a thick layer of ice, it releases latent heat, pinning the temperature of underlying plant tissue exactly at 0 degrees Celsius and preventing further drops.
Alternatively, viticulturists use physiological techniques like delayed winter pruning. By waiting to prune until the terminal buds begin to swell, the growers sacrifice those top shoots to the frost, utilizing the vine's natural acrotony to keep the lower, basal eyes dormant and protected. Modern frost management requires a synthesis of these methods. Growers must balance active thermodynamic intervention with the natural physiological growth habits of the specific crop. While farmers use heat and water to fight frost, Hygrophorus species defend their winter territory through the secretion of potent secondary metabolites. These chemical weapons are called hygrophorones. They are a family of highly specialized fatty acid-derived cyclopentanones unique to this genus. Hygrophorones exhibit potent fungicidal properties against major agricultural crop pathogens, including Fusarium and Phytophthora. In this microscopic view, you can see fungal hyphae secreting a chemical barrier that actively halts the growth of competing parasitic fungal spores. The Herald of Winter maintains its ecological niche through this targeted biochemical arsenal. It effectively suppresses any weakened competitors attempting to establish themselves in the thermally stressed environment. The mechanism behind this defense lies in the molecular architecture of the compound. Look at this animated diagram. The core of the hygrophorone molecule is a functionalized 2-cyclopentanone ring system. The exact substitution pattern on this ring is critical. Watch as the functional groups, specifically hydroxy or acetic oxy groups, snap into place exclusively at the C4 and C5 positions. Attached to this structure is a characteristic alkyl chain. Notice this long, zigzagging aliphatic chain, ranging from 11 to 17 carbons in length, attaching directly to the C5 position. Small structural variations in this oxidized side chain dictate the specific bioactivity of the individual hygrophorone variants against different pathogens. The ecological survival of Hygrophorus is architecturally linked to its ability to synthesize these precise, oxygenated 5-membered ring scaffolds in a freezing environment. To transform these rare, forest-derived isolates into scalable agricultural fungicides, chemists must map out and replicate their total synthesis in the laboratory. The primary challenge in synthesizing hygrophorones lies in their stereochemistry. The molecule requires the precise construction of 3 contiguous stereogenic centers to function correctly. To achieve this, researchers employ the sharpless asymmetric dihydroxylation protocol. In this rotating 3D molecular model of hygrophorone B12, you can see the glowing chiral centers, indicating how this protocol unambiguously controls the absolute R and S configurations. Immediately following synthesis, the molecular connectivity and stereochemical purity are verified using advanced analytical techniques like nuclear magnetic resonance spectroscopy and high-resolution mass spectrometry. Mastery of this asymmetric synthesis allows chemists to move beyond natural limitations, creating designer hygrophorone analogs with structurally tuned properties for increased efficacy against plant pathogens. Late spring frosts act as a brutal environmental filter. For vascular plants, the outcome is rapid osmotic dehydration and cellular death. For specialized fungi, it triggers chemical dominance. We are now translating that fungal defense mechanism into human technology, exploring the use of synthesized hygrophorones as a next-generation class of commercial fungicides. The synthesized hygrophorones are taken from the laboratory and applied via a high-pressure agricultural sprayer across a commercial vineyard. These bio-inspired compounds demonstrate effectiveness against highly destructive agricultural pathogens, including Botrytis cinerea and Fusarium graminearum. By mimicking the winter fungi, agricultural science can protect vulnerable perennial crops from the exact pathogenic threats that seek to exploit their weakened state following a frost event. As climate change forces earlier bud breaks and erratic temperature swings, developing integrated, climate-resilient frost management frameworks has become an urgent agricultural necessity. The future of crop protection relies on the intersection of biophysics, organic chemistry, and chemical ecology. By studying how the Herald of Winter thrives in freezing temperatures, researchers have extracted a viable molecular blueprint for future crop resilience.
This cinematic sweep over a vineyard at dawn shows active wind machines operating in tandem with bio-inspired molecular defenses to ensure crop safety. The ultimate goal of modern frost management is clear. We must translate the biochemical mastery of extreme weather specialists into the ongoing safety and stability of our global food supply.